different phenotypes. Some is more solid, some are more fluid, and based on that, you can see from my animal data that it's very sensitive to this doubles, and the collagen concentration is not double. So the mechanical property is just more sensitive to those ECM compositions. And I hope that the question you raise is the future of this, where this technology can apply into real diagnosis. What I'm studying is how this technique can have most valuable information for the future diagnosis.
So what's the benefit of 3D collagen gels? So why you choose collagen?
Collagen, because I'm studying breast cancer. Breast in the extracellular matrix of breast tissue is mainly collagen type 1 and mainly. So that's why I choose collagen.
Oh, so you mentioned a lot of advantage of 3D gels in the 2D culture. So did you compare the stiffness of cancer cell culture on 2D petri dish and also in 3D culture?
You mean the stiffness of the cell?
Right.
I'm measuring the stiffness of the ECM around the cell. So you're talking about measuring cell itself. So I'm not doing that. But I bet there's many people doing this in this area that I mentioned, the cell stiffness and things like that. But when my level and your level can combine together, we will have much more comprehensive understanding of this biomechanics in cancer.
So can this technique apply to the cell stiffness measurement?
No, the ECM, the extracellular matrix around the cell.
But I mean, why cannot be applied to cell? Why?
Yeah, why?
Why can't you use this for cells also?
Yeah.
Cannot shear that small. Cell is around 1 to 10 microns, so the wavelengths cannot be that small. But in optics, some people do that, because optic tweezer and vibrate the cell membranes, you can measure that. But in my technique, it's in this level, not this level.
Can you increase the frequency in order to decrease the frequency?
If collagen represents, if I further increase the frequency, the attenuation will be so high, which means when the wave is generated, it will be all attenuated by the collagen, because matrix exists.
So I think the question is that what is the volume over which you are getting the average value? I think that's not clear.
What the volume?
Yeah, I mean the number you're reporting is over a certain volume, right?
Yes.
What is that volume? Is it like
It depends
half a
on
centimeter? Is it a millimeter? What's that volume that you're reporting the average stiffness of?
Okay, so if we use this model-based, I'm assuming a homogeneous sample. So I'm getting one value for the whole tissue.
And that includes the cells. So
Yes.
when you say ECM,
Yeah.
it actually includes the cell information.
But in the frequency range I don't think the cell plays much important role in this, because it cannot shear that much. It's like a boat on the sea. When the wave comes, the wave cannot change it. The boat doesn't play an important role in changing the wave, right? But if you shear quicker, smaller than the boat size, you're starting to feel the boat exist.
Okay, so I thought that with the OCT you are doing that. I mean, you are
Yeah, I'm
moving
shearing.
very fast, right?
I'm shearing very fast, but
Right.
still not that fast.
So what's the scale? What's the numbers? What are the dimensions?
It's several hundred microns.
So again, what's the size of your sample?
In the tissue sample, it's usually 1 centimeter to 3 centimeter, and in the gelatin sample I made it bigger, several centimeter, and in the collagen sample, because collagen is very expensive, I cannot use that much, and it's about millimeter.
I was I got a little bit lost when you were going over your OCT acoustic force setup. Are you putting like some kind of the force that's being applied to the sample? Is that a pressure wave or?
Yes, compression wave. Yeah.
And what's that being applied by, like a speaker or?
By an ultrasound transducer.
Oh, okay.
This blue thing is the ultrasound transducer.
All right.
The ultrasound transducer produces this force field, and I'm changing the voltage I input to the transducer, so the force will be sinusoidally changing with the voltage I gave. So the force is changing sinusoidally, so the sample should be wiggling up and down sinusoidally.
Cool.
Yes, you can understand why your technique cannot measure the stiffness of the cell in the matrix. Because you said the resolution of displacement sensitivity is 10 nanometer. But cell, I think regular cell is 10 micrometer, something like that. Why?
But one thing
Because the cell is much stiffer than the matrix, or the wave cannot shift that much, or?
First, I'm not applying the force directly to the cell. I'm relying on the wave generated by the force. When it's propagating through the cells, it's like a boat on the water wave, if you think. So maybe you're right, the cell might play an important role, but in here, ECM plays a more important role in, are you talking about use only cells, no ECM?
No, because your cell is cultured within the
Yes.
3D gel, right?
Yes.
If you apply a wave, so the wave definitely shield the cell and the matrix, right?
Yeah.
So I'm just very curious why this technique cannot measure the stiffness of the cell itself.
Yeah, but when the collagen exists, when the matrix exists, do you expect your wave to be sharing the collagen or sharing the cell?
Both.
Both, yeah, right. Might be both, yes. So
Yeah,
that's
so
why
the
we want to
question
go
is-
to higher frequency to share cell more, and then to see more cell incorporate into this. But in low frequency, I don't think cell plays that important role.
And it depends also on your density of cells, or the number of cells.
Yes,
And
yeah,
the
right,
speed of
right,
sound and
yeah.
So if the cell is a very high complex. If you look at the volume fraction, but the cells could be playing a role.
That's definitely. Cell has cell interaction. That interaction is another force that could contribute to the mechanical property.
Okay. Yes, one more. What do you want to say?
So are
This
you
is like your prelim almost, right?
Yeah.
You're ready for your prelim.
Are you like able to sort of direct or target a certain area in your sample? Do you know like the specific spot you're measuring, or are you just sort of saying the whole?
We're measuring everywhere that the wave propagate to, because when the wave propagate to there, the wavelength is depend on the cell. The wavelength is depend on the material property, like this equation. And there's some other technique only look at the force, the center of the force, and this different technique. In this technique, I'm measuring where the wave can propagate to, and not where the waves are.
Yeah, I think it would be very useful to somehow quantify clearly the resolution, the spatial resolution as a function of frequencies and other parameters. Yeah, that maybe you can highlight very clearly what that
Okay.
is. Yeah. That,
Thank
that
you.
answers a lot of the questions.
Yeah, this is very
But
useful.
That's great. That's very nice work. Any other questions? Okay, great. Let's. Very nice talk. Thank you.
Thank you. Thank you for all your questions.
So we have pizza outside. Please ask more questions.
Before you went on your computer, I had a meeting and I missed essentially your entire talk. But
You have a meeting with me?
oh no! Like at 12 o'clock, I had a meeting and I missed like your whole talk. So could you like give me a short paragraph on like how you did? Because I'm very